And we're going to move to the next speaker. Our next speaker is Geoff Penington from Stanford. He's going to talk about replica wormholes and the black hole interior.
Okay, thank you very much. Share my screen. Okay, is that working? Can people hear me, see the screen, stuff like that?
Great.
Yep, okay. Awesome, so yeah, thank you very much to the organizers for inviting me to give a talk. My talk is called Replica Wormholes and the Black Hole Interior. It's about this paper that came out last November, which was with Steve Schenker, Douglas Stanford, and Jianbin Yang. And there was a paper that came out the same day by Almiri, Hartman, Maldacena, Shagulian, and Tejadini. And really, a more accurate title for this paper would be Section 2 of Replica Wormholes and the Black Hole Interior, because that's all I'm actually going to talk about. Douglas is going to be talking next, and as part of his talk, he might talk a bit about some other aspects of the paper. So what is the sort of claim of this paper? It's very simple. It's that we can successfully calculate the page curve for an evaporating black hole just from a gravitational path integral. And a more precise version of this claim in this talk, I'm just going to be talking about a very highly simplified model. It's not really an evaporating black hole at all, but it is a black hole with an information paradox. And the advantage of that model is that we can do very, very precise calculations in it. You can do the full path integral in that model and so on. And so we can really calculate anything you might want to calculate. But it really seems to be the case that the sort of basic story of how these calculations work is very general. It applies to higher dimensional black holes, applies in flat space, it applies whatever. So yeah, one thing that is really worth emphasizing is that the sort of arguments and ideas I'm going to be using came out of ideas from ADS-CFT. But really, when you actually think about it in terms of the gravitational path integral, there's no reason that you need to have a CFT, that you need to have string theory, you need to have anti-de Sitter space or anything like that. This is really just a calculation that involves the sort of low energy effective field theory, the gravitational path integral. But it needs to be, the rules for that effective field theory needs to include a sum over arbitrary space-time topologies. And in particular, it needs to include topologies containing what are called space-time wormholes, shortcuts through space-time connecting distant regions. So I'm not going to talk about them in my talk, but you can actually use very similar arguments to the ones that give you the page curve to show that not only do you have a page curve where the entropy starts going down, but you also actually have information escaping from the interior of the black hole into the Hawking radiation. Very complicated and cleverly designed operators acting on the Hawking radiation can in fact learn about stuff that seems to be in the interior of the black hole. So this is something that Douglas will talk about a bit. But yeah, for my talk, the first thing I really want to do is just introduce and motivate this sort of simple model we have. And really the motivation for it, as I say, is just to, we really think this is pretty much the simplest possible model you could have that meaningfully has black holes and has black holes with an information paradox. But in order to motivate that, then I'm going to have literally one slide talking about the actual traditional information paradox and evaporating black holes in flat space. So, this of course very familiar story, but let me just go through it very briefly. Okay, so for an evaporating black hole, you have Hawking radiation, and that Hawking radiation is entangled with a sort of partner mode that sits inside the interior of the black hole. And as the black hole evaporates, then you get more and more Hawking modes coming from closer and closer to the horizon. They're entangled with more and more interior degrees of freedom. And eventually, you reach this point called the page time, where the sort of entanglement entropy between the Hawking radiation and the interior modes seems to be larger than the Bekenstein-Hawking entropy of the black hole. Now, whether this is a problem or not depends on what you think the Bekenstein-Hawking entropy is. But if you believe that it is truly the sort of statistical entropy of black hole microstates, it's really counting the number of degrees of freedom that describe the entire state of the black hole, not just its horizon or something like that. And that's certainly something that seems to be true in string theory and ADS-CFT. Then this is a paradox, because there aren't enough black hole degrees of freedom to be able to purify the Hawking radiation. So at that point, you sort of only have two possible resolutions. You either need Hawking's answer that information is just actually lost, the S matrix is not unitary, or you need the sort of, this calculation where the entanglement entropy keeps going up to break down and the entanglement entropy to start decreasing at or before the page time, such that the entanglement entropy always remains bounded by the Bekenstein-Hawking. And this is the answer where you get a page curve, and that's obviously what we're going to find in this talk. Okay, so now we've sort of extracted out the essential features you need to get an information paradox. Then we can try and throw away all the annoying technical details, things like 4 dimensions and so on, that make it hard to actually do path integrals. So we want to make a gravitational model as simple as possible. What's the way to make quantum gravity easier? Well, you just go to fewer dimensions. So what's the fewest number of dimensions where you can have a black hole? It's 1 dimension of space and 1 dimension of time. So we're going to be considering one-sided eternal black holes in 1 + 1 dimensions. And if you have a one-sided black hole in 1 + 1 dimensions, you need to have the sort of space-time end somewhere. So we're just going to have it end on what's called an end of the world brane. This case is it's a 0 brane that the space-time just ends on. Okay, so that was the Lorentzian space-time. We can also consider its annular continuation to Euclidean time. And in this case, we see that the end of the world brane now goes out to the boundary. And that's good because that means we can sort of create this end of the world brane state by preparing it with a Euclidean path. That's in fact what we're going to do. Okay, so now we need some analog of Hawking radiation to actually create an information paradox. So one way you could do that is just add some matter fields to this 2D model. But even that's kind of annoying. You have to deal with quantum field theory and so on. There's an even simpler way. You're just going to add internal degrees of freedom that are just going to sit on the end of the world brane. These are modes, degrees of freedom in the interior of the black holes. There are interior modes. And then we're going to maximally entangle them with just some external quantum mechanical reference system. So I'm going to be a bit more concrete about that. So these internal degrees of freedom on the end of the world brane, you can think of as just having a large number of different flavors of end of the world brane. We can label by I, and then we have these set of microstates, psi I, where we have an end of the world brane in state I. And then we're just going to construct by hand. This is not happening from the dynamics. This is just the state. There basically are no dynamics. This is just a state that we're building completely by hand. A state where we have sort of, a superposition of psi I tensor some reference system in state I, where I is just some canonical orthonormal basis for the reference system. Just construct this highly entangled state. And then we can get our very simple version of the information paradox. You just take the number of states k of the end of the world brane and the reference system to be very, 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 very large. Bigger, in fact, than e to the Bekenstein-Hawking. And then naively, seems like the entanglement between this end of the world brane and the reference system is bigger than the Bekenstein-Hawking entropy. We have exactly the same information paradox that we had before. Okay. So that's all great. We seem to have an information paradox. This model is simple enough that we're just going to be able to, actually compute the entanglement entropy properly. And when we do that, we're going to find that this naive entropy that can be arbitrarily large is not the sort of real entanglement entropy, and the real entanglement entropy obeys a page curve. Okay. So the first way I'm going to get this answer, it's a very simple way that uses this rule for computing entanglement entropies in gravity In this context, known as the island rule, it's really a special case of something more general called the quantum extremal surface prescription. And hopefully, I was actually asleep because it was at about 3 a.m. California time, but hopefully this is something one talked about this morning. So what does this rule say? It just says the first thing you need to do is you need to find all technically quantum extremal surfaces that are homologous to the thing you're trying to find the entropy of. Okay, and then you're going to take all of these extremal surfaces and you're going to look at each of their generalized entropy, this quantity that's like a sum of area over 4G Newton plus entanglement entropy across the surface. The extremal surface that has the smallest generalized entropy is called the minimal quantum extremal surface. And the rule says that its generalized entropy tells you the entanglement entropy you want to compute. Okay, so how does this rule apply in our case? Well, in this case, we have two extremal surfaces. They're codimension 2, so they're just a discrete number of points in 2 dimensions. The first extremal surface is just the empty set. And the second is just, in this case, is a classical extremal surface that sits at the bifurcation surface of the black hole. What are their generalized entropies? Well, the generalized entropy of the bifurcation surface is area over 4G Newton, so the Bekenstein-Hawking entropy of the black hole, plus the sort of entanglement entropy of this dashed line region. And there's no bulk degrees of freedom in this dashed line region, so that's 0. So the full generalized entropy is just the Bekenstein-Hawking. What about the empty set surface? Well, in that case, its area is 0, doesn't contain a point. But now this dashed line region contains the end of the world brane. And that end of the world brane has an entanglement entropy that is given by log k. So the generalized entropy of this empty set is log k. Okay, so put those two things together with the rule I just gave, and we get an answer that the actual entanglement entropy is given by the smaller of log k and the Bekenstein-Hawking. Log k we call is the naive Hawking answer. So this is the page curve. So great, that's the answer. We're done. Very simple model. There we go. But this at the moment, this is a bit unsatisfying because this is just some arbitrary rule that I just claimed was the right thing to do. But the good news is that this rule wasn't just made up out of nowhere to give the right answer. I guess in some sense, the original version of it, the Ryutaki-Nagi formula, the original paper sort of was made up to give a sensible answer. But going back to Lukowitz and Maldacena in 2013, we've understood that these sort of rules can be just derived just using a gravitational path integral. And this is a derivation that's sort of really very closely related and morally analogous to the derivation of the Bekenstein-Hawking entropy using Euclidean path integrals. So in some sense, it's slightly mysterious that this low energy effective gravitational theory sort of knows about these quantities, but there is a long history of it doing so, and it will in this case. So really the rest of this talk is just going to be showing how that derivation works in the case of this very simple model. And I'm actually going to sort of do this derivation 3 times at increasing levels of precision. First going to just do the derivation at the level of the sort of topological part of the JT gravity action. And that's going to be enough to give us a formula for the page curve that's sort of the smaller of log k and the 0 temperature entropy of the black hole. Then we're going to get a bit more precise. We're going to look at the sort of geometry of the leading classical saddle. And that's going to get us the formula for the page curve I gave before of the smaller of log k and the actual Bekenstein-Hawking entropy of the black hole at that temperature. So including the finite temperature corrections. And finally, because it's such a simple model, we're actually going to be able to do the full path integral, not make any assumptions about being far away from the transition point or anything like that. And going to get this somewhat more complicated looking formula for the entropy that involves this function R that is really just the solution to an equation that you need to solve numerically or approximate or whatever. But this formula is in fact non-perturbatively exact in an appropriate limit, in the limit of a large black hole, basically. And it corresponds to the more naive page curve that we'll get from the simpler calculations, with non-perturbatively small corrections far away from transition and sort of a bigger correction that smooths out the sort of kink that you get at the transition. Okay, but before I can talk about any of that, we need to talk about how you actually compute entanglement entropies from a path integral. Because this is a sort of non-trivial thing to do, right? What a path integral lets you compute is things like expectation values of observables. But the von Neumann entropy is not an expectation value of an observable. But fortunately, it's closely related to some things which are called integer n Rényi entropies. So they're given by this formula. But the important part of this formula is this trace of the reduced state on the radiation to the power n. And that is, in fact, an observable. It's at the expectation value of an observable, but it's just the expectation value of an observable on n copies of the system. The observable in question is the Hermitian operator that commutes those n copies of the system. So this is something we can calculate with the path integral, and then we do this clever thing called the replica trick of just calculating this for arbitrary n as a function of n, and analytically continuing that function to non-integer n, and taking the limit where n goes to 1. Take this formula, take the limit n goes to 1, apply L'Hopital's rule, you'll get the von Neumann entropy. So that will give us the answer we want. And the sort of key idea, the thing that's going to enable this sort of simple, very standard answer to give such a counterintuitive result that disagrees with the sort of Hawking answer, that when we do that gravitational path integral, we're going to include topologies that connect together the different replicas via space-time wormholes. Okay, so these different replicas are just independent spacetimes that are not directly connected using classical geometry, but they're going to get dynamically connected together in the bulk via space-time wormholes. Okay, so let's start with just the simplest thing you might want to calculate, which is the purity, it's called. Trace of rho squared. Okay, so this is a step towards being able to calculate general Rényi entropies and then eventually von Neumann. So to calculate this, we just use a Euclidean path integral. And the Euclidean path integral just has certain fixed asymptotic boundary conditions, standard rules for doing gravitational path integrals. And the boundary conditions are determined by the sort of formula for the state that we had before. And in fact, they're this. And so what we have is, because we have two copies, then we have two asymptotic boundaries. And the asymptotic boundaries have end of the world brane at one end in state I, and in the other end in state j. And then we're going to sum over I and j. So now we need to consider the different sort of geometries that can fill in those asymptotic boundary conditions. And the most obvious one is that you just have two copies of something that looks like the original black hole. Okay, so the first thing to note about this particular geometry, topology even, is that we have end of the world brane that up here is in state I, and down here is in state j. Okay, so this contribution is only non-zero if those two states are the same. It means this double sum over I and j is really just a single sum because only the diagonal pieces contribute. That means it gives us one factor of k from doing this sum, but we had a 1 over k squared out the front here just from the definition of the state. And so the overall answer, once you calculate everything and normalize by dividing through by the normalization factor, which in this case is again just two black holes, then the gravitational action all cancels between numerator and denominator, and we're left with a final answer of just 1 over k. So a purity of 1 over k roughly corresponds to a von Neumann entropy of log k. So this is the naive answer. As we take k bigger and bigger and bigger, the entropy just starts increasing and increasing and increasing, seemingly going on forever. Except that there's also another topology that matters. So what is this topology? Just the two black holes are now connected together by a space-time wormhole. Looks like this. So what is the gravitational action of this topology? Well, the Einstein-Hilbert action in 2 dimensions is just the Euler characteristic. The Euler characteristic of this thing is just a disk, so it's 1. But in the normalization, we have 2 disks, so it's 2. So that gives us an overall gravitational action that looks like e to the minus s0. So this space-time wormhole contribution is tiny. It's non-perturbatively suppressed in G. But it's like a tiny, tiny instanton effect. But the important thing to note is that now this space-time wormhole in state I is just connected to another space-time wormhole in state I. It's not connected to one in state J. So that means when we do this double sum over I and J, there's no reason that they have to be the same. We get a full factor of k squared from the sum. That cancels out this 1 over k squared. And we find that this tiny space-time wormhole contribution doesn't decay to 0 even if we take k to infinity. Even if we take the limit where naively the amount of entanglement between the end of the world brane and this external reference system is infinite. Then the entanglement between the black hole and the reference system still seems to be finite. It still looks like roughly the Bekenstein-Horty entropy. Okay, so that's the purity. But yeah, there's an important point here, which is that this quantity, this calculation has some weird features. And the key one is that there was no reason to get these saddles that we needed to sum over I and J. We could have also found the same saddles if we were just computing the inner product squared of psi I and psi J, the overlap of these two different microstates. This wormhole topology is telling us that is non-zero even when I and J is different. There's some tiny exponentially small overlap between these two seemingly orthogonal microstates. So that's a pretty reasonable thing to think happens in gravity. But there's a much weirder thing, is that if we just computed psi I psi j rather than its modulus squared, then we would find that that's 0 when I is not equal to j. We can just do the full path integral in this very simple model, and there's just no geometry, there's no way for the I to be matched up with another I when we're just computing the inner products itself rather than its modulus squared. It's called a factorization problem. We're computing something squared, and we're not getting an answer that's equal to the thing itself, what you get when you compute the thing itself and then square the answer. The explanation for this is just that the gravity calculation, at least in this simple case, is not actually calculating an inner product in a single quantum mechanical theory. It's actually calculating the average of an inner product across a whole ensemble of theories. On average, this inner product between the two microstates is 0, but it has small random fluctuations. And so its average modulus squared of its average, the average of its modulus squared is non-zero. Okay, but we're really not interested in the purity, we're interested in the von Neumann entropy. So let's go to calculating that. This is going to be our first very simplified answer. So in general, for trace rho of the n to the n, there's a lot of topologies that can be important. However, in the limit where k is sufficiently small or sufficiently big, then there'll just be, in fact, one family of topologies that dominates. For small k, the dominant thing just comes from n independent black holes. Just like for n equals 2, then it came from 2 black holes. This is just because this has the largest gravitational action. It has the largest Euler characteristic. So again, the gravitational action cancels between numerator and denominator. In this case, in the numerator, we only have one sum over I. In the denominator, we have n. And so we get a final answer of 1 over k to the n minus 1. This gives, we'll take this answer, you take its log, divide by n minus 1, analytically continue to n equals 1. you get an answer for the von Neumann entropy of log k. What about a very, very large k? Well, in this case, the dominant contribution is going to come from the sort of leading topology where all the different end of the world brane indices can be independent, and so it doesn't get suppressed by any factors of k. The answer for what that topology is this multi-boundary connected wormhole where they're all connected together like this. Euler characteristic of 1. In the denominator, we have something the Euler characteristic of n. This gives an answer of like e to the minus n minus 1 s naught. Analytically continue, get the von Neumann entropy, and we get an answer of the entropy is equal to the 0 temperature entropy of the black hole. However, so far we have only considered the topological part of the action. JT gravity, you have other terms. So let's try and make this calculation a bit more precise. This is going to be our second attempt to the von Neumann entropy, and we're now going to actually look at the geometry of the leading classical saddle. Looks like this. So the key thing to note is that this geometry has a cyclic replica symmetry. If we commute all these different boundaries around in a circle, then we preserve the geometry. So what does that mean? It means we can quotient out by that symmetry and just look at one of these little wedges and imagine gluing this thing here to this thing here. This now almost looks like the original black hole, except that we have a conical singularity from this fixed point. In the limit where we take n goes to 1, i.e. to get the von Neumann entropy, that singularity vanishes and we get back the original unback reacted Euclidean black hole. But very close to n equals 1, you have a tiny back reaction. And it turns out that the von Neumann entropy is just given by the area of that replica fixed point, which in this case is the bifurcation surface. So this is the original trick that Lukowitz and Maldacena used to compute these sort of things. And it tells us that actually it's not just S naught, it's actually the Bekenstein. Okay, so finally, this is going to have to be somewhat quick because I don't have terribly much time.
Sorry, you have 4 minutes.
Yeah.
Sorry, 4 minutes.
Yep. Okay. So we want to actually compute the sort of full von Neumann entropy using the full path integral. So now what I'm going to assume is I'm going to assume that both K and the Bekenstein-Hawking entropy are very large, but I'm not going to make any assumptions about their ratio. So what topologies matter in this case? Well, it turns out it's the ones that are planar, that can be drawn. It can be drawn in on a single sheet of paper. Why is that? So for example, this one we have planar topology that contributes in this limit. But in this one, we have sort of a handle sitting here, and that handle decreases the Euler characteristic, and it means that this topology gets suppressed relative to this one by e to the minus 2s naught. So we can ignore it. Here we have one where it doesn't have any handles, but we have overlapping things that's no longer planar. And in this case, you can count the number of independent end of the world brane states we sum over, we get an answer that's suppressed by 1 over k squared. Okay, so now we need to do this full sum over all the relevant topologies, and then we need to analytically continue the formula to n equals 1. So it turns out that's kind of hard, but there's this beautiful trick that was found by Jembin that goes back to some tools from free probability, and that involves using this thing called the resolvent matrix. It's just defined here, just the inverse of lambda minus rho, but it can equivalently be written as a sum over powers of rho to the n. So graphically, it corresponds to doing a sum over path integrals with different boundary conditions with different numbers of boundaries. Or in the bulk, summing over all bulk topologies with the correct boundary condition. So the clever trick is that we can just reorganize this sum over topologies in terms of the number of boundaries, other boundaries that the first boundary is connected to. So this term is including all the terms where the first boundary isn't connected to any other boundary. And so that just looks like one boundary sitting here, and then just a copy of R, an arbitrary number of boundaries doing whatever else they like. And then we have higher powers that look like this. The path integral for these topologies can be computed, just given by this slightly complicated formula. And the nice thing is that its dependence of n just appears in the power of this function. The other dependence of n just comes from the power of R. Again, it's just power of n, taken to the nth power. And so we can just do this infinite sum by evaluating it as a geometric series. And that gives us this quite nice equation for R, which here is R here is the trace of the matrix we had before. And the great thing is that this resolvent, this trace of the resolvent matrix, in fact, encodes not only the entanglement entropy, but in fact the entire entanglement spectrum of the state. Why is that? Just by using Cauchy principal value theorem, then the sort of density of states is just given by the imaginary part of this resolvent. So if we can solve this equation, we're basically done. We have everything you possibly want. You can't actually quite explicitly solve it, but you can certainly solve it numerically. And it's also, there's a very good approximation that consists of taking just a thermal spectrum, cutting that thermal spectrum off after k eigenvalues, and then just shifting it slightly. I know I'm basically out of time. I will be done in like one more slide. Just to make some comments about the final answer, you can actually calculate the page curve up to really quite small corrections, order G Newton near the transition, and in fact far away from the transition up to exponentially small corrections. And in fact, you can compute those exponentially small corrections. Near the transition, you get pretty large corrections to the sort of naive page curve that smooth out the transition. These corrections are actually significantly enhanced compared to sort of naive non-gravitational time models. The enhancement comes from the fact that you have fluctuations in the energy of the black hole. So here is just the actual page curve, numerical in black, our approximation is dashed, and compared to sort of a naive page curve you'd see for something like a random state. So really very, very final slide. Why bother doing this much more complicated calculation when we basically already got the right answer for the page curve just by looking at the leading classical saddles? It is, after all, just a stupid toy model. The first answer is because we could, and it was fun, and it involved a lot of cool tricks. The more reasonable answers is that there's some interesting physics in these enhanced corrections. Some recent papers by Mao from Wang and Dong and Wang that talk about the same phenomena in higher dimensions for related quantities. So it's pretty universal physics, not just in this toy model. These non-perturbative corrections to the page curve very far from the transition are also really crucial to making the result work. Goes back to a paper by me and Patrick Hayden from a couple of years ago. And it's also evidence that we should really take this full gravitational path integral seriously. Like it's really, beyond just some leading classical saddle, it's really giving us sensible answers. And in fact, the sensible answers it's giving us have very close correspondence with the answers you get from random tensor network calculations. So that's some reasons think that we should really take seriously the sort of random tensor network toy models as genuinely saying something deep about ADS, CFT, and quantum gravity. So yeah, sorry, I ran a couple of minutes over. Thanks very much.
All right, thank you. So let's thank the speaker for a very nice talk. And we have a few minutes for questions, please. Please raise your hand. But there got to be some questions. Okay. Okay, Ronak Soni. Oh, Edward Witten. Yeah, Edward Witten, please.
I'll defer to Ollie a second. Okay, yes, Sony. Tell Sony to go ahead first.
Ronak Soni, please.
Hi, sorry. Why should you not, so in the replica, in the Renyi calculation, the Zn upon Z1 power n? And why should you not consider connected topologies in the denominator?
Yeah, it's good. So in the denominator, all the connected topologies are suppressed by either powers of k or, well, they're all suppressed, in fact, by both powers of k and powers of e to the s. So the limit we're working in, where we take k and e to the s naught both to infinity, but keep the ratio arbitrary, then yeah, there's no non-trivial contributions to the denominator.
Okay, thanks.
Okay, Edward Witten.
Can you say a word about what you meant at the end about how the gravitational path integral gave answers similar to random tensor networks?
I'm afraid I think my internet went a bit bad there, but as I understood the question, it was about this connection with random tensor networks that
Yeah.
I mentioned on the final slide. Is that right? Yeah. So the basic answer is that this sum over planar topologies. So we can in random tensor networks, you can do a calculation by using this thing called Schur-Weil duality, where you replace integrals over unitary ensembles by sums over permutations. And the permutations involved are basically in one-to-one correspondence with these planar topologies. They're both classified by what's called non-crossing partitions. And in fact, there's a more precise statement, which is if we look at the sort of fixed area state or fixed energy version of this calculation, we look at sort of microcanonical rather than canonical version of it, then the full sum over topologies gives exactly the same answer as you get with just looking at a random state. And that generalizes in sort of higher dimensions to fixed area states, you get exactly the same thing you'd get from a random tensor network. So this is discussed in Appendix E of our paper. Can maybe, yeah. But basically the different ways of gluing together a gravitational path integral correspond to the different terms in this Schur-Weil duality sum.
Thank you.
Okay, Andy Strominger.
Yes, so Ashokson computed universal log M corrections to the entropy in 4 dimensions, which are determined just by the massless spectrum of particles. And so one would expect log M corrections to the page curve. We looked at log M we looked at corrections using the island rule prescription in some 2D models and got answers which at the log M level seem to be self-inconsistent. I'm wondering if you think that this formalism can be used, but the results we found could just be attributed to the model isn't consistent. But one wouldn't want to say that about 4-dimensional black holes in the sky. So I'm asking whether one can get log M corrections which shouldn't depend on microphysics out of this kind of analysis.
I would hope so. I'm afraid I haven't read your paper carefully enough to be aware of the details of the problem. Certainly hope you would. Yeah, like you know, there's a question of like sometimes the island rule itself is too naive, but the replica trick will give you the right answer. So certainly. Yeah, it's possible that's the honest answer is I don't know. That's a very interesting question. I'll have to look at your paper and
well, I'm not really asking about my paper.
Yeah.
I'm happy with the resolution that our paper is trying to describe a model that doesn't exist. I'm more asking whether it might or might not be. I'd be happy if that were not the answer. But the more
I would say in this model
is whether one can get it for 4-dimensional Schwarzschild, log M corrections to page.
Yeah, the answer is, I mean, yeah, within this model, you obviously don't have any massless particles, and so it works out right. I would certainly hope so.
I'm talking about the real world.
Yeah, I know. I haven't done the calculation in the real world. I would hope so, but who knows without doing the calculation.
All right, let's thank the speaker again.